Okay, we're moving along here. We're in week 3, and we're adding 2 more points of what we're going to talk about with the meteorology. The ones we're going to go into now are vertical motion, stability, and then from that, adding in moisture. These are going to be the basis for everything else that you're going to learn in this course. So we're going to try to focus some of these on a little bit today and see where we get from here. So vertical motion. Well, any air parcel is going to move all over the place. It's going to go up, it's going to go down, it's going to go horizontally. I mean, typically, if you were to look at a leaf that's blowing outside or whatever, you would see it moving in all different directions as it's moving along. That motion is very critical to understand. Uh, we've been talking about wind being horizontal motion. Well, there's a vertical component to that motion. So that's why velocity is a vector in many ways. It has speed, it has direction it's giving you, and that direction can be up, down, to the left, to the right, north, south, and all that. If you're going to understand where the air parcel is going, and which implies what that air parcel might do, such as will it be cooling or will it be warming, will it be able to generate a cloud, or maybe it's going to lift your plane up, or how it's going to affect your plane. We've got to understand all that. And today we'll talk about vertical motion. We've talked about wind. A lot of the same things apply to vertical motion. Pressure gradient force, geostrophic motion, friction, all of that can influence vertical motion as well. So this vertical motion, just think of it as the air parcel being lifted somehow or sinking somehow. It's just an up and down component to the air parcel. And this vertical complacement can both lead to clouds and cause clouds to dissipate. We'll talk about how that happens as well. And turbulence can develop from this vertical motion. So let's take a look a little bit at a weather map. We're talking about convergence and divergence as being two things to increase vertical motion. We've talked about winds and how they respond to pressure gradient. Here is a low. It's sitting to the southwest of West Virginia, has a warm front to the north, to the east of it, across southern part of Virginia, cold front to the south of it, probably running down through here, down through Mississippi and Alabama and all. So now we've got right north of that warm front, we have south winds coming up and turning in towards the low here. We've talked about friction causing the winds to gradually turn towards the low. And we have a lot of winds coming from the south and then moving almost directly to the east, coming from the east and even northeast into this area. There's a lot of low-level convergence going on right in here. So you think about that, that means the air, at least at the lower levels of the atmosphere, is being pushed to rise. Uh, there, and vertical motion can take place anywhere in the atmosphere. It doesn't necessarily have to start at the ground level. It could be up above the ground where it's starting. So, but in this case, it's definitely starting. You can see it at the ground level here. Lots of air pushing towards each other. Just look at the barbs on the wind coming into this area, then another barb coming up into this area. So there's all that air that's coming in here. You have convergence. Where there's convergence, air's got to rise. Above that, we'll look in this triangle area. Let's take a look at Maine here a little bit. You can see you have like 10, 15 knots of wind moving to the west here, and only 5 knots or so coming down and sinking down here. So you actually have air kind of leaving this area, divergence. So you're actually causing sinking motion. So that's just another aspect where you have convergence to the one area around the storm. Around high pressure, typically you're going to have divergence. So another thing we're going to talk about is fronts with how they can be influenced by the mountains. So in this case, we have a cold front that's moving across here. You actually have along the ocean here, you can actually see a little bit of a kink to the isobars here, trying to develop a front right in this area here. So you're getting a good convergence along that front. You have southwest winds and then southerly winds here. And you probably have some instability there as well, helping to lift the air as well. So you're still seeing the good lift, and you're seeing the precipitation fall out in this part of this area. Back here in West Virginia, And this happens frequently into the mountains and the Appalachians here. You see all the northwest winds coming out of the Great Lakes and then down. They're hitting the mountains here and they're rising. They're being pushed up. So you're winding up getting the rising motion there caused to the topography, the orography of the area. So we're going to talk a little bit about stability too. Stability influences how fast vertical motion is. You can get convergence and you can get divergence to push the air up. But if you get the extra component of stability, say you get you're unstable, you have instability, that can increase that speed up tremendously. So that can have a major influence on the amount of clouds, strength of mountain waves, the sea breeze, where they'll even form showers or thunderstorms with it. So what you're looking for is basically a change in density of the air parcel as it's moving up. We've already talked about, pressure equals density times the constant times temperature. Well, if that density is lower than the air around it, and warm air is less dense than cold air, we've already talked about that as well. So say you were pushing in that, when you saw along the warm front, the cold front there, excuse me, over the eastern part of the U.S., we were looking at it on the previous slide, right here, that area probably has a lot of warm air coming up into it from the Gulf Coast region, Gulf of Mexico here, the Gulf Stream probably pushing some warm air into it as well, moist air. So there's lots of warm air rising right in here. Around it, you have colder air probably. So that instability, again, is what's generating. The air is less dense. It's going to be going up. So it's probably going up faster than it would have been if it was stable. So we're going to look a little bit about this. We're going to take a look at a couple different atmospheric ways of looking at trotting these things in the vertical. On the left-hand side here is pressure, all the way up through 1,100 millibars. On the bottom is temperature in degrees Celsius. And you have moisture, solid line going up to the left in the greenish color here. And it's basically moisture is going to be plotted as vapor pressure, 0.1, 0.2, all the way up to 20 grams per kilogram of vapor pressure. So let's take a look at a chart then that's been filled in for Lake Charles, Louisiana. So we've plotted the moisture, and where the moisture and the temperature are the same, you wind up with 100% relative humidity, which we're going to talk about more in the next chapter. But you basically have clouds forming. Here they separate, so they're further apart. And you can see here, you can see the lapse rate, the temperature, how it's decreasing with height, with time. And then it begins to increase. And we'll go back to that in a second here. Let's see if we get back there. Here we go. Right here. And that's where the equilibrium level is. We actually could argue that's right about in here is where the stratosphere may begin to influence, but more likely probably up in here as well. But there's at least a stable layer right in here as well. If you had thunderstorms developing, they'd have to get through this stable layer. They might have a difficult time getting through there. And that, you look at the elevation here is approximately, 9,300 meters, about 30,000 feet up right there. So that would be about where you would expect the highest thunderstorms might get at this time. And we're talking, temperatures rising with height here. But looking down low, the temperatures are actually cooler. We've talked about, down at the low levels of the atmosphere in the boundary layer, sometimes we get both warming and we get cooling. And this is a early morning sounding. It was done at 7 o'clock in the morning in January. We had a little bit of cooling at the bottom of the sounding, a little bit of cold air going out. So you can see that how high the cold air got. It wasn't real high. It was only, if you took off in a plane, you would very quickly get back into the warm air. But there is a little layer there. And this is something you can see the winds were light. So that's something to just keep in mind as well when you look at soundings like this, you can actually see the layers, where the warm air is, where the cold air is, and stabilities with that. And vertical motions, we're talking about stability here. Say I bring this parcel of air right here. Let's start rising that parcel of air. Well, that parcel was moist, probably fairly warm. It's going to have be just a little bit warmer than the actual air around it here. So it's probably going to be rising up at least into here. But if I'm pushing it, if I have good convergence down in here to push it, I might actually get that parcel to continue all the way up right into this area as well. And the next chapter, when we bring moisture into it, you're going to discover why that air partial is really going to accelerate and head up. So we'll do that in a minute here. So we've talked about parcels and instability and how they tend to rise faster when they're unstable. And just think about a hot air balloon. If you were to put more heat in that balloon, the faster it's going to go up. Less heat, less it's going to go up. When you're looking at clouds, sometimes you can actually guesstimate or make an estimate of what type of vertical motion might be going on in those clouds. Some clouds are very flat, like stratus clouds, stratiform clouds. When you're looking at them, there's probably not a lot of strong vertical motion in those clouds. They're just slowly rising. So it's something to think about, that you're probably fairly stable maybe in most of those stratiform clouds. However, when you get the bubbly ones, the ones that look like they're even in the middle of the atmosphere, there's some cumulus clouds that can form at 10, 15,000 feet up. It means it's pretty unstable up there probably. Even in the morning, sometimes you see those, and those are days when you got to look out for severe weather, possibly. Look out for, if there's enough moisture around to start generating thunderstorms and towering cumulus, they may easily hit that unstable layer aloft and just continue to rise. So let's get away from this one now, and let's go into moisture. So the moisture we'll talk about. Let's go into right here a minute. And there's atmospheric moisture would be the atmosphere would be so much easier to forecast without moisture. Moisture changes state, and that causes all kinds of problems for pilots, for meteorologists as forecasting the weather. It just so happens that our natural range of the atmospheric temperatures causes the water to change from a liquid to a gas to a solid and back and forth. And every time it does that, it changes how the remaining part of the atmosphere is affected. So, first off, what is changing state? Like say it's condensing. When water is condensing, that means it's changing from a vapor, which has a lot of energy. You think about gas. Gas always has more, when it's in a gaseous state, it always has more energy because the molecules are moving around so fast. They have a lot of energy. When they go to become a liquid, they have less energy. That's how I always thought of it, and I thought about that, and then you go all the way to a solid, they have even less energy. So in order to get to those states, they must lose energy somehow, and that energy is called latent heat. So when something is changing from the ice to water is melting, then you've got to absorb latent heat. The ice got to get some more heat into it, like you would see on a wintertime day when you have snow outside. And if the sun's hitting that snow and it begins to melt, it's absorbing heat. That's the latent heat that's causing it to melt, change state. Another one, of course, is water to water vapor, evaporation. Again, you can see that as well. Again, it's gaining heat, that water. It can go the other direction as well, all the way, sublimation. Every once in a while that occurs, and it goes all the way from ice to water vapor. That takes a lot of heat, a lot of energy, but it does occur, and it's something to remember that's occurring. And it's a major source of energy for the atmosphere. So without it, there would not be that much energy that's going on. Some of the things we see happening would not be happening. So let's take a look at a cloud. Here's a nice thunderstorm going up. That cloud's experiencing a lot of different latent heat as it's going up. As the air rises and cools, latent heat is going to be released. First off, below it, there's no water, so they're probably going to be becoming a liquid. So you're going to be changing water vapor into a liquid. Therefore, you're releasing latent heat into the atmosphere. Guess what? You just made this air parcel warmer by giving some heat to it. So that air parcel that now is wet, and you see around the thunderstorm is all dry, is probably warmer than the air around it. So it's going to be going up faster. Now you continue on up, and guess what? You're going to start seeing ice at the top of this cloud. Water can freeze really starting about minus 10 Celsius is where it really starts picking up and freezing. So when it does that in that area, you're changing from liquid to ice. Again, more heat's released, even more than is released from going from water vapor to a liquid. So it's even warming even more, and that's why it continues to rise, this instability here. Yes, there's probably been heating down below it, helping to lift it up, get rising motions, vertical motions going up, but then all of that kicks in. So you have changes of releasing of latent heat as it's going up. Now, as that air comes back down, when that thunderstorm begins to drop rain, that air is going through dry air coming on down. And some of that rain is going to begin to evaporate. But when it begins to evaporate, guess what? It's cooling. Its energy must be coming back into it. So the dry air around it's losing energy. So that means that by losing energy, it's actually cooling that air parcel coming down, the raindrops. That's how you get the downdraft forming. It becomes more stable and starts accelerating towards the ground. And here we have the continuation of that with the thunderstorm and the reverse processes. So any gas has a vapor pressure. We've talked about vapor pressure before. You should look at a tire. It has a vapor pressure. How much of it, depending on how much pressure you put in that tire. And each gas in that tire, say you have the nitrogen, you have the oxygen, you have some water vapor in there, you probably. All of that contributes to a total vapor pressure. But we're going to just look at one component of that vapor pressure. We want to know the water vapor pressure. How strong is that water vapor? How much moisture is in the air? The higher that vapor pressure, the higher the amount of moisture in the air. Because a given air parcel can only hold a certain amount of water. The colder the air parcel, the less water it can hold. The warmer the air parcel, the more water it can hold. So, as that air parcel cools, its saturation vapor pressure is going to begin to drop. And you're going to wind up possibly having condensing that water vapor that's in the air parcel. So another way of looking at all this is relative humidity. You've all heard it. If you have 100% relative humidity, the air is saturated. It has reached its saturation vapor pressure. If it hasn't, if it's less than 100%, it has not reached that saturation vapor pressure. The drier the air is, the more moisture that air can hold, and therefore the further away from condensation it is. Dew point's just another measure of looking at moisture. The higher the dew point, the higher the moisture. And these are always reported in METARs. The difference between the dew point and temperature, that dew point depression, the larger this is, the drier the air. The smaller it is, the more moist the air. One of the things as a meteorologist we'll look at nighttime is see how that changes. If you're expecting fog, for example, you'd be looking at how close are these values getting with time? Are they getting closer and closer to each other? Or have they even got to the same, where there's a 0-degree dew point depression? When that happens, it's very likely fog will form. Another thing to think about with dew point depression, if you drop rain into the atmosphere, that rain is probably cooling. The temperatures are trying to go down to the dew point because they want to be 100% saturated. We're bringing moisture into the air. Temperatures are going to go down and dew point's going to go up a little bit. Well, sometimes in the wintertime, you may be very close to freezing. And the actual temperature might be 33. The dew point might be 15. And say it starts to rain. Well, as that rain comes down, the temperature and the dew point are going to come up, but maybe that temperature is only going to go, maybe temperature is going to drop 4 or 5 degrees, and so instead of being 33, it becomes 29, and maybe the dew point went from 14 degrees Celsius all the way up to where it was up to freezing, 14 degrees Fahrenheit, all the way up to freezing, and you wind up with freezing rain instead of rain. So that's something to look at with the temperatures always, and dew point, the spread there. Different things you can infer from that every time you're looking at it. Clouds are interesting in that the water droplets have to form. You look at your wings of aircraft or on ground surfaces, and you get dew, and you touch it, and they begin to form once the RH is 100%. And remember, conduction plays a role in this as well. Right next to your wingtip, it might be very colder than maybe next to the ground. So that could cause the dew or even a frost to form on your wing before it actually forms on the ground. So we're talking about cloud formation. We've talked about getting the air through this moisture comes into it through evaporation, and this can move with the wind flow. Well, we've already just talked in the last chapter about vertical motion, so that wind begins to go upwards sometimes. So wind off the water can even bring more water vapor in with it, or wind off a desert, maybe you have less water vapor. One thing water vapor likes to condense on is what they call condensation nuclei. Condensation nuclei are basically some form of dust, sea salt, and they actually condense quicker on it depending on what type of dirt it is. For example, sea salt will actually cause condensation at a higher temperature, than clay would. So you wind up getting more clouds close to the water than you might get over land, further inland sometimes, even though the amount of moisture may be the same. And then there are also the ice condensation nuclei, which triggers the freezing within a cloud that forms the snow and the ice crystals. Almost all precipitation begins as some form of snow or ice, and then begins to melt as it comes down and changes into rain. So yes, you can see the cloud forming, and that is basically condensation that's taken place that causes your water droplets there, but the precipitation itself was probably going to begin as some form of snow or ice crystal. And here we go again with cooling it off as it's moving up. Moisture-laden air can touch a cool surface. Adiabatic cooling, when you expand the air, it cools as it's rising upwards. And because of the latent heat releases, we can change the lapse rate with this. If you had a dry adiabatic lapse rate, that means the parcel is never saturating. And that parcel is basically going to cool at about 3 degrees Celsius for every 1,000 feet you go up. So if you lived in the valley and wanted to, let's take Beckley, for example, and let's go up in the mountains there. You're going to start out, say, at the bottom of one of the mountains there at, say, 1,000 feet. And if you were to go up 2,000 feet, you would have cooled 6 degrees Celsius. That's about 9 degrees Fahrenheit. So you're about 9 degrees colder than you would have been. So if you started out at 70, you'd be down about 61 by the time you got up to the top of the mountain. So that's just, something to think about. And it applies as well to how, saturating the air. The air parcel that got saturated could be cooling slower than the dry air parcels around us, and thus it could be more unstable. And we've just looked at that with the thunderstorm. Here we're back into that same diagram, and you can actually see. Let's take a look at it now. Here you have saturation. So if I'm going to lift the saturated air parcel right here, well, that saturated air parcel is not going to want to cool that fast. So it's going to go up what they call the moist adiabat, which is probably right about in here. See this curved line right here? And that's where it's going to go up. And all of a sudden, you'll notice the temperature, we'll take it 400 millibars. Well, gee, I'm almost, 10 degrees Celsius warmer than the air around me. So that parcel's gotten pretty doggone warm as it's gone up there, compared relative to the air around it. So if it's that warm, it's going to really be wanting to rise up very quickly. Yeah, eventually it's going to hit this layer and maybe slow down, and then its layer doesn't cool as fast. So, oh, okay, so maybe I'll wind up topping out in here. But I've got some really strong vertical motions probably going on, anywhere from 500 millibars up to 300 millibars right in this area. And the max vertical motion is probably going to be just before it reaches this stable layer here. So that's something to think about when you're looking at soundings. And hopefully you will look at them as you're looking to make a flight somewhere to see how the atmosphere is changing. Here's a Skew T log P. It's a typical sounding used by meteorologists. The reason it's used is you can easily determine something called convective available potential energy. All that is how warm the air parcel can be compared to the actual temperature of the air. If you look at the curve here, what you find is temperature is skewed. That's why they call it QT. The pressure is plotted as a logarithmic function from 1,000 to all the way up to 100 millibars. And then you have the moisture, which is just a dew point plot versus the actual temperature plot. So let's say if we brought it up here, the question is, where would these things saturate? And it may take a lot. It's really a relatively dry sounding here, looking at this sounding, so it might not be saturating very easily. But again, it's always interesting to find your vertical motion, find where the moisture is going up. One other thing with this sounding you can look at is Ski. They call it the hodograph. All it is, you saw last week we were looking at wind roses. Well, think about a wind rose. Your direction and your speed is a circle. So here's 10 knots, here's 20 knots, 30 knots, 40 knots, all circles. So if you had a west wind, you come out here at the ground 10 knots. Oh, you have a little stronger west wind when you get up to 1,000 feet. That'll be out here. Well, maybe by the time you get to 6,000 feet, you have even a stronger west wind. So basically what you've done is make a plot. That's a straight line in this case. So you have if you were to talk about wind shear, you would say, oh, there's a very strong wind shear here because the winds kept increasing with height significantly. But they're not turning with height, which would be something you would want to know. Clouds can tell you a lot. We talked a little bit about that with some. If you look at a METAR and you see different height layers, what's being reported, one of the deficiencies in a METAR is you don't actually get the cloud types. It would be very interesting to know the cloud type many times, just to know what that cloud might be telling you. METARs are just reporting the base of that cloud, how far they can see into it, but they're not telling you how high that cloud is or what its structure looks like. But it's still a good first estimate as to what, sometimes it's nice to know that the height of that cloud maybe is 500 feet up or whatever. When you're looking, for example, for thunderstorms development, you can look at the sounding in the morning and say, oh, I might get cumulus clouds developing maybe at by mid-afternoon, probably around 4,000 to 5,000 feet. Well, if you actually see them, maybe they're started earlier in the day and they're at like 2,000, 3,000 feet. Well, then somewhere some extra moisture got brought into these soundings in your air mass you've been looking at. So that METAR just told you that, hey, that sounding wasn't telling you the whole story. So now all of a sudden you can begin to estimate, well, maybe I have more moisture. That might make it more unstable. Now maybe I have more thunderstorms around. So METARs and clouds are telling you a lot of information. METARs also report the horizontal visibility. Horizontal visibility is mainly affected by moisture, such as fog, such as snow. Snow reduces visibility rapidly compared to rain. And this is just some more information about how METARs estimate the different cloud types. So again, just looking at when you're flying, Observing the clouds can tell you a lot. They can tell you where maybe a land sea breeze might be set up. They can tell you, oh, there's some cirrus coming up from the south. Oh, maybe I've got a warm front that's moving north from down there. Or maybe I'm seeing blow off from thunderstorms down there. Anything you can learn from a cloud is very important. Satellite images, great tool, a great way to begin to understand what's going on. And we have both GOES satellite, and beginning in the fall, you're going to start seeing GOES 16 data. One of the things I was working with, what they called GOES-R, which is now GOES 16, there is a lot of information available that's going to become available from that satellite. Some of the things will be such things as literally every minute they'll be able to have a picture of the Earth hemisphere. They'll be able to see both a infrared, a visible, and we talked about radiation at different levels. Well, it turns out that things like water vapor and different gases radiate and are concentrated in certain levels of the atmosphere. If you know what levels they're concentrated in, you can actually look for that radiation, that signature. So maybe you can pick out, oh, this is probably at 10,000 feet, or, oh, maybe this is at 20,000 feet I'm looking at. And maybe you can pick from that radiation then and see how the clouds might be moving in that area. So a lot of information is available. We also have polar orbiters, which go across and they can see a lot of information. Wind speed at the surface, they can actually pick up over water, for example, from polar orbiters. Many polar orbiters actually will look at and be able to do some soundings into the atmosphere, so actually get some kind of information on temperatures, moisture, and all, and even winds at middle of the days instead of just twice a day, like we get with the balloon soundings. That's also something with the aircraft nowadays with the soundings. And we talked a little bit about precipitation forming. You need them, the dust and the things. There's some processes that take place to really allow the precipitation to reach the ground. Yeah, we need the condensation, the deposition on the particles. Then there's something called collision coalescence. This means the particles are just bumping into each other. If you have vertical motion, you have a turbulent motion. It's not all, oh, a nice smooth flow. Every air parcel is moving exactly the same speed. They're moving at different speeds. And it won't take much. They just like bumper cars. These particles are just bumping into each other. These raindrops are bumping into each other. And all of a sudden you wind up with a big raindrop, big enough that where the air is moving up, it's still too big to be held up. It's going to start dropping. It's going to come down and it's going to rain on you. Another area is freezing occurs once it starts freezing in the upper atmosphere. And ice crystals, the actual vapor pressure over an ice crystal is always such that water will want to go to the ice crystals. They want to make the ice crystals bigger and bigger, where they're going to go away from where the cloud droplets would be. So you build these ice crystals up, and it begins to snow in the upper part of the atmosphere. Then they start the collision coalescence, bouncing around each other, and eventually get down where the atmosphere is warm enough, and they're going to fall down on top of you, and it's going to rain. So let's take a look at a route today. And I really wanted to take a look at the East Coast today. This is where I think the weather's kind of interesting today. We'll just look at a satellite picture right now. And you can see here this upper level trough flowing through there. You can actually see it moving with time, spinning right in this area. This is water vapor. So we see this dry air right here. And what you're actually seeing is the stratosphere, kind of some of its air mixing in. The stratosphere is very dry. So you're seeing some of its air mixing into this layer right in this area. So this is where if you look at the contours on 500 millibar charts or other charts, they're going to be low right there because they've pushed in very cold air probably right in this area. And this is the center of it right here. So this is building on, helping to generate vertical motions. And you can actually see the moisture. If you were to track the moisture back here, you can see it comes all the way off Pacific Ocean, across the mountains and then down into the area. We're not really getting a lot of moisture coming from the Atlantic Ocean or anything into this. So let's take a look at the infrared at the same time. Infrared is just temperatures of the clouds, the top of the clouds. So how cold is the top of the clouds? Well, you can see here the bluish area. That's the colder part of the cloud. So let's take a look at how it's changing. You can actually see with time, this area has had it actually been enhanced. So there's more and more vertical motion going on. Clouds are cooling. Probably kind of a low pressure beginning to develop here. We're going to look at the surface. At the same time, you can see there's a lot of low clouds right out here because we were looking at the infrared and we didn't see any enhancement on those clouds, did we? So what you're seeing actually is low clouds. Tops are low and the bottoms are low probably. So there's probably a lot of low clouds in this area with this upper level system. Up in here, you're seeing snow on the ground. So let's continue on. Take a little route here. So let's go from, how about Charleston, South Carolina? We're going to fly up this evening to Binghamton, New York. Looks like a great route. So you're going to want to know what's going on right now. Well, we've just looked at the satellite, and it says there's enhancement of precipitation along here. You've got a weak area of low pressure. Kind of looks like right along the East Coast. You have a warm front you're going to have to be crossing along the way. But you also have a pretty good cold front here. Good northwest winds. Temperatures are in the 30s behind it and in the 50s out ahead of it. So there's over a 20-degree temperature drop there. So what does the forecaster say about this then? Well, take a look at a couple things. Let's take a look at the radar. We think of national radar, look at it. All that enhancement there. But there's another band right here. We noticed that earlier. We saw that enhanced rain area there. Enhanced trough, deep low pressure, aloft right in this area. That's going to be generating a lot of convergence out ahead of it right in here. So let's see what it does. Oh, pushes that cold front down and begins to develop that low. Where we were seeing that before, now we're seeing a much stronger low developing. We got lots of precip all of a sudden, and the blue indicates there's some snow up in here. Moderate snow, maybe. Now, it doesn't last long. Moves off the coast. And this is by morning, it's gone. But we're thinking about going up here to Binghamton this evening. So we have a problem. We got to deal with this potential right there. If we're leaving Charleston, we're flying across the cold front. We have a low pressure here. So we have several issues right there we need to deal with. So let's take a look at some morning soundings too. Let's see if we've got any instability out there. One of the very nice things. All right. Yeah, let's take a look at the convective outlook. Well, look at that. This evening, there's marginal chance of a thunderstorm, even severe thunderstorm out there. And that's not much, but there is still a chance. So maybe we need to be taking a gander at instabilities and see just what we're dealing with. Instabilities in the atmosphere there. So let's take a look at a sounding from that area. So this is Morehead City. Morehead City is located to the east of our path right now. You can see it's got lots and lots of moisture. Tons of moisture in the sounding right now. All the way up. Here's where your tropopause develops almost up about 250 millibars or so. Then you also see the nice curve to the sounding a little bit. Instead of being a nice straight line, it's a little bit curvy. So let's move up with this sounding. Let's take a look at Pittsburgh. Just out of curiosity. Whoa, look how much colder that sounding got. Way, way colder, much colder aloft here. Doesn't have any of that moisture in it. All right, so this air, if you'll notice, the winds are out of the west and dropping south in even northwest. So we can look at Blacksburg for a minute. And what we're seeing is there's a lot more cold air, very dry, adiabatic kind of air. All of a sudden, when we start listing air parcels into here, they may become unstable, particularly from about 500 millibars on up to about almost up to 250 millibars. So where we had some, vertical motion from that upper level trough coming in, we have some convergence at the low levels, and now we're going to begin to lift it. And it's not very high amount of vertical motion or instability, but there is some. So that marginal area is beginning to look like maybe they were caught up to something there. And there's a couple other things we can look at from the Storm Prediction Center. I talked about how strong that wind looked and how it was. Well, here's the jet stream. Here's a 120 knot jet coming down into this area. This was this morning's sounding. So when it comes down like that, it causes what's called divergence aloft. And you'll look right over this area here. That means the air right here is diverging. Now, this is at 200 to 250 millibars. So we're talking, 30 to 40,000 feet up. Well, if the air is going divergent there, somewhere below it is probably converging because the air doesn't want to, doesn't like losing air pressure up there. So it's going to want to fill that gap in. So there's air coming right into that area, and that's where we're seeing the showers develop now and those possible thunderstorms. So as we're going to be taking this route sometime, we're going to be knowing that this is going to be coming into our route, something we want to deal with. That's just something to keep in mind as we're moving along here. So we can look at air. Let's take a look at 850 millibar temperature advection. Wow, there is very strong cold advection out here to the northwest. And we have some warm, not much in the way of advection to the east. So all this cold air is coming in at 850 millibars. That's helping to cool this atmosphere right in here, helping to make it more unstable. Let's take a look at 500. See if we are 700 millibars. Let's take a look up there a little bit. And we can even see it there coming in as well, cold air advection right in this area, helping to cool some of this atmosphere down. So all these are ingredients for potential to start seeing some thunderstorms in this area. And sometimes it's nice to look at what they call frontogenesis. And frontogenesis just means there's a front trying to form there. Doesn't mean it's formed yet. But let's take a look at around 850 millibar frontogenesis. And we have a front literally forming at 850 millibars. So if you were to say, oh, we had that cold front that looked like it was out a little bit ahead of that, well, there's a front aloft right behind that as well coming in. All that's feeding, what that means is the air is tending to converge in this area, and we see the showers and thunderstorms developing here. So it's just a nice picture of what's happening with time. So we're going to move forward now a little bit and just see, what the clouds are doing. We saw on the upper air, I wanted to look at that a little bit just to see what, we saw how low the clouds didn't look very high. Well, man, look at all the IFR and stuff up in this area to the northwest of that front, north of that cold front. Lots of low clouds up there. And north of the warm front. Well, what do you get north of the warm front? Well, you have warm air that's aloft, going to be tending to rise. It's going to cause cloudiness. So the shallower that cold air is at the surface, the lower these clouds are going to be. So again, we're going to have that to contend with as we're flying into this area. These are all things we got to take into account as we're flying north tonight with time. So we can look back here with time. One last quick peek at one thing. We'll look at the simulated reflectivity at this time. And simulated reflectivity is just that. It's simulated. It's an estimate of what the radar is going to look like. It's one of my favorite things to look at, just because it will tell me, We see these showers. We see them out there now. Look at them, how they develop and enhance as they're coming east with time, moving in right across our route. And Binghamton itself probably has some light snow, but be all right. And the timing of that, well, say I wanted to go up there around 7 o'clock tonight, I'd have to go through all of that. And then it just becomes more of rain showers and all in this area. So maybe if I delayed it a little bit, I might be better off. I come out ahead behind it. Skies might be clearing, the low is moving away. You can actually see the rotation to that low with time out over the water here as well. So you can see how the vertical motions have all played in. Notice all these little dots of showers out here. That's because there's some instability out there. The model's picking up on it. There's really cold air at the low levels down here rising up, causing it. You also see the lake effect. Warmer air coming off the lakes, getting pulled into the circulation with moisture, latent heat being released, little convection developing. And then you see the low actually forming with the showers here at the circling back around. So I hope you got some information from this on how you might plan a flight, begin to look at some things, begin to understand a little bit about vertical motion and how that works with things, and also how moisture is beginning to move into here. So if you have any questions, please let me know. Hope you have a good week.